Okay, good morning. So last class we were discussing uh, mathematical preliminaries, and specifically we were in the middle of this topic of quadratic forms. So quadratic form is basically a generalization of a quadratic function to multivariate functions, right? When it's a homogeneous function, you don't have the linear terms, and generally it's expressed in terms of a matrix A, right, which whose elements become the coefficients of various terms in this function. So it is expressed as an x transpose Ax, where A is a square symmetric matrix. So A can be a general square matrix, but we take it to be symmetric because of this reason I explained last time. Even if it is square matrix that is not symmetric, right? The expression that you get will be effectively equal to, suppose A is not a square matrix, not a symmetric matrix. The expression is same as the expression you will get for this, right? So this is symmetric matrix. So therefore, we just take it that quadratic forms are always discussed for square symmetric matrices. Now, this is useful to understand the concept of a minimum and a maximum for multivariate functions, because later in the course we'll very often try to look for maxima or minima of multivariate functions. Right? For that, we need to first be able to understand what does it mean. Because in case of 1D function or univariate function, it's straightforward, somewhat straightforward, because you just have to look for the first derivative, where it goes to 0, and then you look at sign of the second derivative, you know whether it's maximum or minimum. But even here, like I was saying last time, it's not that simple, because you have situations where the first derivative is 0, but second derivative is right. It's also 0, and you don't know whether it is maximum or minimum. It's the inflection point. So you have situations, but where first derivative is 0 and second derivative is non-zero, life is simple for univariate functions. So, but what is the equivalent concept for multivariate functions? So, with that question in mind, we expanded the multivariate function around some point x naught, where the gradient is 0, and then we observed that the shape depends primarily on the second order term. Okay, small h transpose capital H, small h, and capital H is the Hessian, which has all the second derivatives. And so now the question is, what is the shape of that function? So before we go to that, let us look at some examples of how to differentiate functions in how to differentiate multivariate functions or functions in multiple dimensions. So we'll try to express these functions in terms of in matrix notation. So x is in Rn. So here b is also in Rn. And then f of x is given as b transpose x. It's a linear expression, sigma bi xi. So its derivative is basically bi. So the vector of all coefficients bi. So that can be given as f trans del of x. This is a notation of a gradient. Del of f with respect to x is equal to the gradient, which is given by the vector b. B consists of right now second derivative is Hessian of f, which is given by h of hij, right, is equal to dou square f by dou xi dou xj. Right, this is not just equal to 0; it's something more complicated than that. We'll see that. So now, if you take quadratic form, that what is the first derivative, what is the second derivative? Okay, so quadratic form, let us take it as half of x transpose Ax. Now, x is a n-dimensional vector, A is an n by n matrix. So then dou f by dou xi, you can show laboriously, right? You can take this expression, for example, as an example, differentiate with respect to x1 and then with respect to x2 and all that. Then you can show that del of f with respect to x is nothing but x. You have quite an elegant form. And hij, this Hessian, dou square by dou xi dou xj, is nothing but the matrix A. No, this is ijth element that is equal to aij. So because this is straightforward to see, because if you look at this expression that we derived in the last class, right? If you take the derivative of this with respect to second derivative with respect to x1 and x2, right? Or x1 twice. X1 twice you get a11. X1 and x2 you get a12 plus a21, which is both are same. So it's you get 2 times a12, and here you get 2 times a11. You differentiate this with respect to x1. So here in this case, since you have a half in the front, right? So if you differentiate with respect to x twice, you get a itself, matrix A itself. Okay. Then another concept, another derivative that we need to get introduced to, I will use it. We don't use it now, right now, but we use it later in the course. Is a Jacobian. Let us say I have a function, not even a function, but a multidimensional function. So the multivariate function f. So here f itself is a scalar, but x is a vector. But what if f itself is a vector, right? And of dimension m. Okay, so then, so f is Rm. So and x is Rn. Then what happens? You can differentiate del of f1 with respect to x, del of f2 with respect to x, and so on. You can differentiate with respect to all the components of it. Okay, so you'll have some m vectors. Okay, so that forms a matrix, and you can see that here. So each row is the gradient of one component of f with respect to the vector x, and there are m such components. So this matrix is called a Jacobian. So we'll use it later in the course. So how do we understand this function x transpose x? How do we geometrically interpret that? Because a quadratic function is easy to understand, right? We have y equal to some ax square. I just know that it is like this. If a is positive, and it is like this if a is negative. So this is very easy to understand geometrically. But how do you understand expression like E is equal to half of x transpose x? What does it mean? So let us do that. For that, let us do a small transformation of this expression into a simpler form where we can visualize it more easily. So since A is a square, real and symmetric matrix, right? We know from a previous theorem that we described in the last class that there exists a orthogonal function or orthonormal function Q, right? So that Q transpose AQ is equal to D, where D is the diagonal matrix of all the eigenvalues, and we know that the eigenvalues are all real for a square symmetric matrix, for a real symmetric matrix. So then let us look at a transformation. X is equal to Qy. Okay, so y equal to Q transpose X, whichever way you take. So if you substitute this in this expression, E is equal to half of x transpose X, x is equal to Qy. So if you plug this in here, you get half of y transpose Q transpose AQy. Now Q transpose AQ, that is nothing but D, the diagonal matrix of all the eigenvalues. So you get half of y transpose dy. So D is this. So therefore I can expand this as simply, so if you see this, it is y transpose dy. I can expand this as half of sigma yi square lambda I. So it's a much simpler form to understand. So now E is a function of new variables y1 to yn, and the expression is simply a sum of independent functions of yi's, right, where each term is simply yi square times lambda I, or lambda I times yi square. So this is a very simple expression. You take each term, but that's just like this, y equal to ax square. So if you look at the variation of the function with respect to these new variables, y1 to yn, that's very simple. If you take the ith variable yi, it simply increases or decreases depending upon the sign of the corresponding eigenvalue. If lambda is positive, with respect to yi, e increases, right? And it's always positive. If lambda is negative with respect to uh, yi, right, e is negative as a function of yi. So if I again take, I have this. If I differentiate this twice, I get lambda. So, so we start with this expression half of x transpose x and rotate it. We get this expression. Now this we can understand. Now what we'll do is, we want to understand. We originally began with the objective of understanding the shape of this function. Okay. Now we have the same function in the new form, right? Which is this function. Let us try to understand this function, the shape of this function. But then you might object because how is it valid to come to conclusions about the shape of the original function, which is expressed in terms of x, right? By analyzing the new function, which is expressed in terms of y. So the answer is, you can see that we obtained this new variable y through this transformation, linear transformation by x is equal to qy. Now we know that multiplication by q, an orthogonal matrix, is length preserving. It doesn't change lengths. So which means if it's not changing lengths, that means you're only rotating the points. But all the points in the input space are simply rotated by this transformation. There is no change in dimensions. So which means what? If you have the function oriented in one direction, you simply rotate in different direction. So mere rotation doesn't change the shape of the function. It's like rotating a ball. So, so therefore we conclude that if the first function has a minimum, here it's all at the origin because the gradient of this function is 0, right, at the origin. So we're discussing basically what happens at the origin. So if the original function has a minimum at the origin, new function also has a minimum at the origin and vice versa. So therefore, it is enough to understand the shape of the new function at the origin, but the same shape is valid and is applicable even to the original function in terms of x. Okay, so now let us try to understand the shape of this function, sigma lambda I y square. For simplicity, let us look at a 2D version, right, where y is 2D, and so therefore E becomes E of y1 y2 is equal to lambda 1 y1 square plus lambda 2 y2 square. What is the shape of this function? Let us look at some examples. So you can see that let me add a slide here. So if you take, P y1 y2 is equal to lambda 1 y1 square plus lambda 2 y2 square. Right. So if lambda 1, lambda 2 are both positive. Okay. So since they're all real, so we don't have too many cases. If both are positive, then the function will be turned upwards like that. Right. And if lambda 1, lambda 2 are both negative, then the function will be turned downwards like that. And so this is x1, sorry, this is y1, y2. Now the more interesting thing is, if lambda 1 is greater than 0 and lambda 2 is less than 0, which is other case, then you'll have something like slightly difficult to draw, but right, so it will be increasing in one direction, the upward curvature in one direction and downward curvature other direction. Okay, so upward curvature is in the y1 direction, and the downward curvature is in the y2 direction. So thing is here, this is a minimum, this is a maximum, right? This is neither minimum nor maximum. So this is called a saddle in a different context, but this is not exactly as, this is kind of like a saddle. It looks like a horse and a saddle that you use on a horse. So thing is, moment you go to, so in this case, the second derivatives are non-zero. In the univariate case, the problem arises when the second derivative is also zero, then you have a difficult situation where you don't know whether it's a minimum or a maximum. It's neither. But in multivariate case, even when the second derivatives are non-zero, if the second derivatives don't agree with each other, that is, some are positive, some are negative, and all that, then life becomes more complicated. You have a situation where the function is neither minimum nor a maximum at that point. So you see the gradient is zero in all these cases, but you don't always have minimum or a maximum. So this is a problem. So we need to define this more carefully, right? So what we can say here is, in the general case where E depends on some n terms, right, n variables, yi to y1 to yn, then only when all the eigenvalues are positive, you have a function which is going up and which has a minimum, and only when all the eigenvalues are negative, you have a function which is going down and therefore has a maximum, right? But the more general case will be some eigenvalues are positive, some are negative, then it is neither. Now, it's obviously whether the function is positive or negative and or has minimum or a maximum, now it depends upon its eigenvalue composition. Right, so this basically is a property of that matrix A. It all depends upon what kind of eigenvalues the matrix has. Right, so based on that, you get this interesting property of matrices called definiteness. So therefore, a matrix is supposed to be positive definite when all the eigenvalues are zero. For all all the eigenvalues are zero. Sorry, are positive. Pi I is greater than zero for all I. So when that happens, the quadratic form for that matrix associated with that matrix, that is x transpose Ax, is zero, is greater than zero for all x that is non-zero. For x is zero, obviously it will be zero. But for any non-zero vector x, right, the expression x transpose Ax will be strictly positive, and all the eigenvalues are strictly positive. Then such a matrix is called a positive definite matrix. And the corresponding Hessian, so if you look at a general multivariate function, and if you want to know whether the at a given point where the gradient is zero, whether the function has a minimum or a maximum, right? If it has a minimum at that point x naught where the gradient is zero, if the Hessian at that point is positive definite. So this is how we apply the concept of positive definiteness to the Hessian, right, of the multivariate function at a given point, to find out if it is a minimum or a maximum. If the Hessian is positive definite, then the function has a minimum. Then there is slightly relaxed concept where you say that it doesn't have to be strictly positive, but it can be positive or zero. So this is called positive semi-definiteness. The matrix is said to be positive semi-definite when the function x transpose Ax is greater than or equal to zero for all x not equal to zero. So this happens when lambda I are all greater than or equal to zero for all I. Okay, so that means for the lambdas which are positive, for the corresponding dimension goes up like this. For lambda is zero, the corresponding dimension is flat. The negative definite means all the eigenvalues are negative. That means the corresponding quadratic form x transpose Ax is strictly negative for all x not equal to zero. Okay, so this is for all I. So this is where we get the concept of a maximum. That means for a multivariate function which has a minimum at a point x, has a minimum at a point x naught, right? When the Hessian of the function at x naught is negative definite. Okay, so you can find definiteness by looking at the eigenvalues of that matrix. Then negative semi-definite is slightly relaxed concept. So when all the eigenvalues are either negative or zero, right, then the quadratic form x transpose Ax either negative or equal to 0 for all x not equal to 0. Then indefinite is the case, like I showed you pictorially, that a saddle, for example, arises when you have the corresponding matrix is indefinite. That means the eigenvalues could be anything, could be positive, negative, or real, positive, negative, or 0. They're all real, but in terms of sign, they can be anything. Then naturally, the expression also can be positive, can be negative, can be 0, or all x greater than or equal to 0. Sorry, all x not equal to 0. So this is example of a saddle. So you can see that for some values of x, it is 0, some values it is positive, some values it is negative. So there's no guarantee, right? And then there is neither minimum nor a maximum at that point. Okay, so these examples you have seen before, both lambda 1 and lambda 2 are positive, function goes up, minimum. Both are negative, function goes down, maximum. One is positive, one is negative, it's a saddle. But the fourth case is interesting, just like what happens in this indefinite case, where some are positive, some are negative, but some can be 0. So take a simple example where lambda 1 is positive and lambda 2 is 0. Then what happens is in the lambda 2 direction, it is y2 direction, it's not x2, it is y2. The y2 direction, there is no variation, it's flat. Okay, and in y1 direction, it is curvature is upwards. So therefore, it looks like a canal, some kind of, just fold a paper, in one direction. This is the kind of shape you get in this case when you have. So this will happen when Hessian is singular, because some eigenvalue or eigenvalues, right, are zeros. So that gives an idea of how complicated the problem of minimum or maximum gets when you go to multivariate functions. Even in the case when the Hessian is non-singular. If it is singular, so if some eigenvalues are zeros, then it gets even more complicated. I mean, I'm not going to the full theory of that. Okay, so now let us look at the next topic, which is optimization. We'll look at only quadratic optimization, right, with and without constraints. Because the reason we discussed quadratic forms is to look at the concept of minimum and maximum. Minimum and maximum means you're optimizing a function, you're finding where it is at the highest value or least value. So let us look at that problem with a constraint. That is, I have a function half of x transpose Ax, b transpose x plus c. X is an n-dimensional vector. But I have an additional constraint. So how do you solve this? So the gradient of this del of f with respect to x is Ax plus b equal to 0. Right? So x plus b is equal to 0. So x is equal to minus b, and you can solve this. Okay. So if assuming A is a non-singular matrix, right, is invertible, then this is the answer. Now you get a more interesting case when you have to minimize some cost function with a constraint, that is, minimize some cost function with a constraint that g of x is equal to c. That is, there is a constraint on the vector x. The x has satisfied the constraint. How do you do that? So this problem is solved using the method of Lagrangian multipliers. We'll just give some pictorial arguments to to explain why this method works. Okay, so let us say I have a function f of x, which you need to optimize, find the maximum value, with the constraint that g of x is equal to c. So for simplicity, so that we can draw some pictures, let us assume that x is in R2. So I give it as two coordinates x and y. Now the f of x, the function is like this hill. Okay, let's assume it's like this hill, and you want to find the maximum. Suppose there is no constraint at all. This point right here will be the maximum. But that's not okay, because I have a constraint. I want to have this function g of x that has to be equal to c. So let us say g of x equal to c will give you some kind of a curve, right, on this. So if you project this line onto the xy plane, you get a curve, right? So that is, when projected here, you can see it on the right picture. This red line, right, is the curve which denotes gx or g of x comma y equal to c. So my solution has to lie on this curve and also should give me the highest possible value of f of x comma y. What is that point? So you can imagine, now you can consider that I take level curves of this function f of x comma y. So f of x comma y has a hill, has a maximum, right, at this point. Now I cut this hill at various levels. So I say f of x comma y is equal to d1, f of x comma y is equal to d2, so f is equal to d3, and so on. So where d1, d2, d3 are increasing values. So I take this this condition f of x comma y is equal to d1, d2, and all that. For every one of those conditions, it's effectively I'm slicing this hill at the level of d1, d2, and so on. So I get, in this case, because it's a simple picture, I get different contours. The contours are shown both in the left figure and right figure. And as the d goes up, right, I'm looking at higher and higher values of d. These closed contours keep shrinking. And ultimately, all these contours shrink, and at one point, which is a real maximum of the function f, right? So as you go up with with increasing d, you approach the real maximum. But point is, so take for example the level curve. So these kind of curves are called level curves. So level curve is basically when you slice a function at some level, you get a curve, and that's a level curve. Okay, in this case, the solution of the equation f of x comma y is equal to some d, d1, d2, whatever. So now let us look at f of x comma y equal to d. So that level on that level curve, f of x y is everywhere d3, right? And it has two solutions on the g of x y equal to c curve, here and here. Okay, but the point is, this is not the highest value f you can get, because I can increase and go further up. So I'll go up to d2. So f of x comma y equal to d2. So here also I have two solutions, here and here, but I can go further up. So you can keep on considering that. If I go beyond d1, right, to some value here, let's say d0, for example, then I get a even higher value of f, but I'm not intersecting the curve g of xy is equal to c. Okay, so the thing is, d1, d3, d2 are good. I mean, they're intersecting, but they're too low. d0 is quite high, but it's not intersecting. So what is the exact that golden mean, the sweet spot, is a level curve which barely touches the g of x comma y equal to c curve. So the level curve, right, and the constant curve g of x y is equal to c should reach a point where they just barely touch, right, or they should have a common tangent. Okay, at that point you have this constraint optimum, an optimum which satisfies the constraint and also the highest value that you can get for f. Now this is a geometrical argument. Now how do you translate this into equation? So you see that this tangent, right? Okay, so at this point you have a common tangent. Okay, so that means the normal of the level curve and the normal of the constraint curve g must be parallel, must be like, they can be in opposite direction, but they must be parallel because both have the common tangent at that point. What does that mean? So I can take it that del of f with respect to x. So this is a normal. So at that point, so I'll call this point some, I don't know, call this point x L, x Lagrangian. Okay, where x is equal to x Lagrangian. That should be proportional. That is, the vector should be parallel to to f of g with respect to x at x Lagrangian. So this is what is required. This is one equation. So I can take it that this plus some lambda equal to this equal to 0, or this minus some lambda equal to this equal to 0. So I can take it like that. So del of f minus lambda del of g should be equal to 0. This is also saying the same thing in a different way. So this is one equation. The other equation is g of x equal to c. This is another equation. The solution will have to satisfy these two equations. Then we are done. Okay, so the same thing happens in this so-called method of Lagrangian multipliers. So e of x comma lambda. So we define this extended cost function, e, which is e, defined in terms of vector x and the lambda, right? So let's take the simple case of having only one constraint function. So we'll have only one lambda. So f of x plus lambda times g of x minus c. So now there are two equations. Del e equal to 0. That is one equation with respect to x. Then del e with respect to lambda equal to 0. So if lambda is there's only so if we have multiple constraints, then we will have a separate term like this for each constraint. If there's only one constraint, then there's only one term, and therefore one lambda. So then this del e with this lambda becomes dou e by dou lambda. Okay, so if you do that, if you differentiate, so if you take this whole thing, del of e with respect to x will be equal to del of f with respect to x plus lambda into del of x with respect to g of x minus c. Okay, is equal to del f plus lambda del g. C is a constant, so I can ignore that. This will be equal to 0, or del of f is equal to minus lambda del g. This is saying the same thing in a different way, right? This is one equation. The other equation is dou e by dou lambda is equal to 0. So if you do that for this expression, because e is given as f of x plus lambda into g of x minus c, so therefore dou e by dou lambda equal to 0 is equal to basically g of x minus c. So g of x minus c equal to 0. This is just a constant equation. Okay, so if you solve these two equations, you get the solution. Let us take a small numerical example. My cost function that I want to minimize, okay, or actually maximize, is this, which is given as x1 minus 1 whole square plus x2 minus 1 whole square. Suppose there is no constraint. The maximum of this occurs when x1 is equal to 1, x2 equal to 1. It's a very simple, trivial problem. Because it's always negative, and the best value it can take is 0. Okay, but things get more complicated because I have a constraint. The constraint is that x1 plus x2 is equal to 1. So now how do you solve this? So your extended Lagrange function is Ex is equal to f of x plus lambda and x1 plus x2 minus 1. That is a constraint. So if you take dou f by dou x as it is, right, del e by del e with respect to x is equal to 0. That is equivalent to dou e by dou x1 equal to 0 and dou e by dou x2 equal to 0. So if you take this for dou e by dou x1, you get minus 2 into x1, right? And this is gone. Plus lambda, so minus 2 into x1 minus 1. So that is minus 2 x1 plus 2 for the first expression. Second expression, it is just lambda is equal to 0. This is dou e by dou x1 is equal to 0. So the second equation is dou e by dou x2 is equal to 0. Third equation is nothing but the constraint. So if you just solve these two, you get x1 is equal to half, x2 equal to half. Okay, so it's straightforward. Now we can use this method of Lagrangian multipliers to interpret eigenvalues in a slightly different fashion, geometrically. So let us take the quadratic form of a matrix A, which is half of x transpose Ax. Now I'll try to find the optima, right, of this function under the constraint mod norm x equal to 1. Okay, so I want to find the optima of x transpose Ax when mod x is equal to 1. So if you take put the constraint, the length of the x is equal to 1, and then try to find optima of that, I get eigenvectors and eigenvalues. How is that? Let us see that. So norm x equal to 1 implies norm x squared equal to 1, which is both the same, or x transpose x is equal to 1, or x transpose x minus 1 is equal to 0. This is my constraint equation. So if you plug that in here, I get this extended Lagrangian function. I'll call this some p prime is equal to the quadratic form plus this constant expression. I put a lambda as a factor, and I put this minus half and all just to get some nice algebra at the end of it. Because lambda is just a factor, so you can put whatever you want here. So I say del e prime with respect to x is equal to 0, this first equation. But differentiate with respect to x, the first expression simply becomes ax, and second expression simply becomes lambda x. So I get ax minus lambda x equal to 0, or x equal to lambda x. This is your famous eigenvalue equation. Okay, and x equal to qi, and the corresponding eigenvalue is lambda I. Okay, so like that you can get you can interpret. So basically, the eigenvalues and the eigenvectors are basically directions, right, or the points that you obtain when you optimize this function, and under the constraint norm x is equal to 1. Okay, so with this background, now we are in a position to solve some interesting or useful problems. Very often, right, in engineering situations, you end up solving system of linear equations, x equal to b. So in your high school, you might have done solve such equations in for 2 variables and 3 variables, like laboriously actually inverting the matrix and things like that, or to some kind of elimination methods and all that. Now we will try to solve that in more general situations for n dimensions using matrix methods. So here there are multiple. So the equation we try to solve is x equal to b, right? X is in Rm, b is an n-dimensional, and a is n by n. This is the most general one. Let us take a slightly special case where n is equal to m, and so you have x. A is a square matrix. X, the equation is x equal to b. I can directly invert A and get this. So assume that A inverse exists. So then the solution x is equal to A inverse B. So this is the simplest case possible. Now we have more interesting cases. When n is greater than m, so that means n is, so what happens is you have a11 x1 plus a12 x2 etc is equal to b1. Okay, and then a21 x1 plus a22 x2 plus is equal to b2. Okay, so you have the dimension of b indicates the number of equations. So therefore, n is the number of equations, and m is the number of unknowns or the variables. Okay, when both are equal and A is invertible, then your simplest case, this you have done in your high school math topics. But when the two are not equal, one is greater than another, or vice versa, then things get a bit complicated. That's where you start using the least squares methods, least square solutions. So take, for example, this case where I need to fit a line through a bunch of points. So like I said, each point, so my equation of the line is, let us say, y equal to mx plus c. Right, but I want this to be equal to, let's say, d, if d is the actual value. So this is x. right, for various values of so x1, x2, and etc. So y is given as m x1 plus c, yi is equal to m xi plus c, and so on. For these various values of xi, the on the line the output value is yi, but I want this to be actually equal to some other value di. So this is yi, this is xi, but this is di. Okay, so it's not possible always, but this is what I want, right? So in this example, like I have 5 data points. Okay, so that means I have 5 equations, but I have only 2 unknowns, m and c. So how do you solve this? So that's what you have here. The n is m is 2 unknowns and n is 5 equations. So then what we do is we resort to the method of least squares, right, solution. That means I cannot satisfy this equation all the time. I cannot just replace yi with di and solve it to get m and c. It's not possible. So what we do is I define something like some cost function e, which is di minus yi whole square over all the data points. So now minimize e. That means minimize e or find m and c so that e gets minimized. So this is a problem statement. You're not trying to directly solve the equation. You're not trying to solve the and minimize the cost function. So same thing in general case, right? Will be like this. So I have I can't solve x equal to b, but I'll try to minimize x minus b norm square expression. So let us look at that. E now can be, so let me see this. So I define E as x minus b norm square. So x minus b norm square is nothing but x minus b transpose times x minus b. Right, so this can be written as x transpose A minus B transpose into X minus B. So if we take all sorts of products, X transpose A transpose A X minus B transpose X plus X transpose A transpose, sorry, B plus B transpose B. So this is the whole expression. Now, how do you solve this? Note that these two expressions are the same because let's say B transpose A is, let's say B transpose A is equal to some C transpose. So therefore, X is equal to C transpose X. Then you know that C transpose X is equal to X transpose C, right? Because this is dot product of C and X, the vector C and vector X. So therefore, that is nothing but X transpose A transpose B. So both are same. So therefore, if I differentiate E with respect to X, you get, so derivative of this, you get a 2 factor out, right? 2 times A transpose AX minus 2 times B transpose AX. So this is the expression, and this has to be set equal to 0. So I get sorry, differentiate X goes away. So you get, so thing is, say this, C transpose X. If I differentiate with respect to X, the answer is C itself, right? Because C transpose X is nothing but sigma Ci Xi So we differentiate, you get the C vector, which is a column vector. So I have this should be A transpose B. So minus 2. Yeah, so this is equal to A transpose B. So X is equal to A transpose A inverse A transpose B. So this is the answer. So this is the least square solution. For this problem. Okay, so where n is greater than m and the number of equations is more than the number of unknowns. Then we have the third situation, so where you have number of equations fewer than the number of unknowns. So take, for example, right, x equal to b. Take as an example. Okay, so this is x equal to b. That is a1 x1 plus a2 x2 is equal to b. Right. So I want a solution for this equation. So obviously, if there's only information given, I can have infinite solutions because any point on this line will satisfy the equation. But that doesn't sound right. So can I have some kind of a constant which gives me a unique solution? Then I'll add a constant which says, give me a point which lies on this line, but has a minimum norm. That is, has the shortest distance from the origin, right? That becomes a unique solution. Okay, so in the case where the infinite solutions, where m is greater than n, right, we can add a minimum norm condition such that you get a unique solution. So we'll see this in the next class. All right, this you can solve for a simple case, like in a 2D case using basic calculus. But for the general case of n dimension, it is slightly more involved. You have to use the method of Lagrangian multipliers. So we'll do all that tomorrow.